What's up, ladies and gentlemen? Hopefully I remember how to make these. Hopefully I remember how to do circular motion. Hopefully you guys being back in the classroom won't ruin my day. No, I'm just kidding. It could never ruin my day. You know what I mean? You guys are pretty chill. You're all right. You're all right. I don't care about what your parents say about you. But anyway, we're going to talk about circular motion today. So, without further ado, um, let's talk about it. So, just kidding. With much further ado, disclaimer. We're not going to talk about all things going in circles today because circles are a very broad topic. There's a lot of circles out there. What we're going to focus on today is uniform circular motion. Since I don't define this anywhere else in this set of notes, I'm going to go ahead and just tell you what uniform circular motion is. Uniform means constant speed, not velocity. And we'll see why in a second, not velocity, but constant speed. So this is not for things spinning and then spinning faster or spinning and then spinning slower. It's for things just kind of spinning and they're still spinning the same amount of spin, you know? So yeah, it's uniform circular motion. All right, let's talk about it. So the first thing we want to know is how the heck do you go in a circle? So we're going to look at a point. Let's make a point. Okay, there we go. Now I got a point. So this point is going to go around this circle like so. And it's going to go at a constant velocity. I lied. Not a constant velocity. A constant speed. Okay. So let's talk about what happens and examine some things, and then I'll tell you how you go in a circle. So when our object is coming around the circle and it's coming around right here, its velocity, it is going that direction around the circle. So here is its velocity. It's pointed 100% in whatever direction that direction is. We'll even call it the positive y direction. Okay. Here is our velocity. It's v1. We don't really care how long it is. It could be 1 meter per second. It could be 1,000 meters per second. It's that much. It's however much. It's v1 much. And it's going that way. Sometime later, our point has rotated around. Because it's going constant speed, v1 is the same number as v2. They're the same length. So this length here is the same length here, but they're not the same velocity. Remember, for velocity, direction matters a whole lot because it's a vector. So because these are pointed in two different directions, we can't say they're the same velocity. We have to say they're different velocities because they have different directions. Okay, so let's examine v1 and v2 and maybe try and figure out what the acceleration is. So I had v1 like this, and now I'm going v2. So what's the difference here? What did I have to do to this one to turn it into this one? Well, I had to do two things. We had to, sorry, let me get a nice color. What color do you guys want to look at? Green? I had all this in the y direction, and now this one has none in the y direction. So I had to accelerate that way, right? I had to accelerate that much. I had to take away that much y for my from my velocity. I had to get rid of this much y velocity. Okay, so I took that much away. So my acceleration, I would be accelerating the opposite direction to cancel it out. Okay. The next thing I had to do with my acceleration is I had to gain some of this x velocity, right? So let's just drag it over. Boom. Okay, so now this green vector is our You're going to have to forgive me. I'm a little out of practice. This is our acceleration, right? This acceleration has the negative y component we need to cancel this out. And it has this x component here that we need to gain this x here, right? And this acceleration happened as our point moved from the right side of the circle to the top of the circle. So where this acceleration is kind of like our, because we're only looking at the very beginning and the very end. We're looking at this velocity where it started and this velocity where it ended, and not necessarily the whole thing going around. This is more like an average acceleration. So average kind of means middle. Yeah, I'm hand waving a little bit here, but the place this acceleration would happen would be right there in the middle. Perfect. Okay. So if I were a little bit better artist, what you would start to notice is let's actually do something fun here. Let's group all this stuff together. Get all this stuff out of the way. Okay. So we could do this for any two velocities on the circle, right? And if I did that, so I could do it for like these two velocities, one here and one here. I could do it starting at the top and then it going down. Do you see how my acceleration turns as I look at different velocities? And it kind of always points in the same general direction. This acceleration is always pointing more or less, right? A little less because I'm a bad artist, towards the center of this circle, right? If I take my circle and I rotate it like this, still pointing pretty much towards the center. If I look at the velocity starting on top and now I'm on the side, kind of towards the center. If I look at these ones, kind of towards the center. If I look at these ones, I lost this, I gained that, kind of towards the center, right? So our acceleration, in order to go in a circle, here's the important part you need to memorize for the rest of your life. To go in a circle, your acceleration must always be perpendicular to your velocity, and it needs to point towards the center of the circle. There you go. That's the trick. That's the magic. Let's talk about why. Because we're going at a constant speed. If my acceleration were, let's say maybe, sorry, I'm getting the nice pretty colors for you. Let's say it weren't totally towards the center. Let's say it were more like this. This acceleration has the towards the middle we need, but it also has a little bit of up that we don't need. So it would add this here, but then it would also make this longer and it would speed it up. So if it's not pointing perfectly towards the center of the circle, it won't just turn it. It will also change the speed. It'll make it go faster, which is not really what we want. Okay. So the trick to go in a circle is have an acceleration always pointing towards the center of your circle. Now let's talk about one more very important thing. Where do accelerations come from? How do we get accelerations is the next important question. How do I accelerate towards the center of the circle? To get an acceleration, we need an unbalanced force because of Newton's second law, right? The sum of forces equals the mass times the acceleration. So forces give us accelerations. So a more intuitive way to think about this is I need a force towards the center of the circle. That's what we really need, is a force pointing towards the center of the circle to get us to turn without speeding up or slowing down. Okay. So let's talk about the net force that's required for this. The net force must always be directed towards the center of the circle. And you're going to say, but what if I don't? Well, then you'll speed up or slow down, and then you won't have uniform circular motion. You could still have circular motion, right? You could still go in a circle, but you'll be speeding up or slowing down, and we're not quite there yet. Okay. The force must be pointing towards the center of the circle, the net force, and be equal to the centripetal force. Okay. We're getting a lot of new vocab here. So, first things first. We only need the net force to point towards the center of the circle. That means we could have 2 or 3 different forces pushing us forward, pulling us back, pushing us sideways, any of that stuff. But they need to cancel each other out so that the total amount of force, the net force, is only pointed towards the center and has a certain size. Okay, that certain size is given a special name. It's called the centripetal force. There are kind of 2 types of forces as far as circles go. For circles, undo. Let's get a color that's visible for us. For circles, there are actually 2 types of forces that we're going to be concerned with in a moment. There are tangential forces. Tangential. I think I spelled that right. Like tangent, meaning like if you have a parabola, right? The tangent just like kisses the outside, just barely gives a little love tap and then buggers off. Same thing here. It just barely kisses the edge and then goes away. Tangential is one type. Centripetal kind of has the same center. So that's the part pointed towards the center. Okay. So we really are caring about this centripetal force right now. We'll dive into it a little deeper a little later, but for right now, the centripetal force is what we're looking for, meaning the force pointing towards the center. And there's a special equation for how big that force needs to be. So if we have some object going in a circle, we take its mass multiplied to its, this might be a little more accurate to say speed. It's speed squared or velocity squared, the number. We don't really care about the direction because we're squaring, and that kind of gets rid of the direction anyway. Divided by the radius of the circle. So from the center to the edge, that's the radius. So the mass of the object times its speed squared divided by the radius, that is how big the force needs to be pulling the object towards the center or pushing the object towards the center so that it goes in uniform circular motion. And there you have it. Okay. Again, there's a little bit more to this. There's some words that we're not quite talking about yet, but this is an introduction. It's baby steps into a big topic. We're just getting your toes wet for right now. So, let's talk about this centripetal force idea a little bit more, just so we can talk about what it is and isn't. So, what the centripetal force is. Okay. It is constantly changing directions. If our object is here, it's pointed that way. If our object is here, it's pointed that way. If our object's here, it's pointed that way. And no matter where you're at on the circle, it always points towards the center of your circle. So it is constantly changing direction. Okay. It is constantly pointing towards the center of rotation, or the center of whatever circle you're going in. And the centripetal force is just a fancy word for the sum of forces for uniform circular motion. It's we'll get to what it is in a second, but it's just a fancy word for the sum of forces when we're doing uniform circular motion. Okay. What it is not a force that goes on a force diagram. So if you are looking at something here and it's going in a circle, you don't put force centripetal on the force diagram, right? Here's weight, here's normal force, here's force centripetal. No, that is wrong. Do not put it on there. You need to, it's like the net force. You don't put a net force on a force diagram. You put the force that's like acting on the object, right? It needs a specific name, right? It could be, maybe it's a ball tied to a rope, then it's our tension force. It could be in a track. You know what I mean? Like we could have a little ball right here. And it could be like rubbing against this wall. So then we'd have like another normal force, right? We'd have a contact force with a physical object. It could be a lot of different things, but it can't be the centripetal force itself. That's a fancy label for another force. What is the centripetal force? It's the tension. What is the centripetal force? It's the normal force from that wall pushing on you, right? What's supplying the force towards the center of the circle? That's what the centripetal force is. It's just the fancy name for the force in a specific direction towards the center of the circle. Okay. It is not a constant force. Here's why it is not a constant force. Force is a vector, much like velocity. So the same way we can't say that this is a constant velocity because it changes direction, we can't say this is a constant force because it changes direction. The magnitude of that force is constant. It has a constant number, right? And that number is whatever you get by using this formula. It is not a constant force, though, because it's constantly changing direction, and direction changes the force. That is a different force. Okay. The other thing is a centrifugal force. Okay. Actually, I have a slide talking about this. It is not a centrifugal force. Centrifugal forces don't exist. This is not a force. This is a bad word. You're not allowed to say that word anymore. Don't say it. If you say it, I'm gonna get mad. Right. I'd rather have you go tell your grandma that her homemade bread isn't even that good. You know what I mean? Like, don't do it. It's a bad word. Okay. So let's talk about this bad word force. Okay. I think the place that almost everyone knows centrifugal forces from is from cars, right? At some point, you are in the car with your mother or father or older sibling, especially older siblings, if you're kind of like close in age and you're in the car while they're learning to drive and they take a corner a little too fast. So here, let's elaborate on this drawing a little bit. All right, here's our road lines. Here's the sidewalk, right? Your older sibling takes this corner too fast. And let's say you're sitting in the back seat, like right there, right? When they turn this corner, you get slammed into the door, right? It's as if you are being pushed that direction, correct? You get pushed into the door and you go, hey, watch it. Learn how to drive. You're an idiot and you're ugly and you smell and you're never going to get married and you're going to die alone and I hate you. Learn to drive, idiot, right? Or as long as you have a healthy relationship with your siblings like I did. Then they go too fast. You get pushed in the car door, and it's as if you're being pushed towards the outside of the turn. You're being pushed away from the turn you're trying to do. Okay, this is the situation, and at some point in your life, someone said, that's the centrifugal force. That person lied to you. There is no such thing as a centrifugal force. That is a fake made up thing, and it doesn't follow physics. Okay, let's re-examine. You are in the car, your sibling is turning too fast, your mom yells at them, and you're in the back of the car. You're right there. Okay. I just told you that if you're going to go in a circle, and this is kind of circular, the force needs to be towards the inside of the circle, not the outside of the circle. So what gives with this seemingly contradictory, paradoxical force that you're experiencing? Okay. Let me maybe help change your frame of reference here. What's actually happening? Let's say your sibling didn't turn. You're here in a car and you keep going this direction. Okay? Cuz you have momentum, which is kind of a bad word that you shouldn't be saying yet cuz you don't know how to say it correctly yet. But you get what I mean. You've got momentum, so you're going to keep on keeping on. You're going to keep doing what you're doing, right? What happened is you're keeping on, and when you got here, your sibling turned, and they put a car door in the way. So now you run into this solid car door that your sibling just threw in front of you by turning the car around you. And now you're running into this solid object. Now this solid object pushes on you perpendicular to its surface. The car door is pushing you towards the center of the circle. You are not being pushed into the car door. Let that sink in, right? I think this is a little confusing. You aren't pushed into the car door. The car door is in your way, and it's pushing you towards the center of the circle because it's solid. And then you start going that way, right? So then the car door turns a little bit more, and now it pushes you that way, right? And the car has turned a little bit more, like this. Crazy, isn't it? So there is no centrifugal force. There's no force pushing you into the car door. You were just moving that direction to begin with. And now someone put this stupid car door in your way, and it's pushing into you because you ran into it. So now it pushes towards the center of the circle and provides a centripetal force, not a centrifugal force. And there you go. And that's how you turn, right? Cool. All right. So there is no centrifugal force. Erase that word from your vocabulary. Every time you say that word, you got to put $1 in the swear jar. All right. Let's do 2 examples just to kind of cut our teeth on this stuff. And then at some point, maybe not today, maybe not tomorrow, maybe not for the next year and a half, but someday you'll have homework on this. So probably today or tomorrow. Probably not a year and a half, but you know what I mean. Anyway, you guys are probably too young to see that movie. Anyway, so let's do some examples just to kind of cut our teeth, calculate some stuff, and then we'll get you on your way. So this is a fast car example. So a bunch of cars are racing around a track, and one of the turns is circular. So you've got a track like this. And everyone knows in fast car, you can only turn right. So you're going this way. Okay. The turn has a radius. Ooh, that's an important word. So from the center of the thing, so like right here to here, this is 40 meters. And your favorite driver is traveling 50 meters per second. It says so on the little like ESBN like heads up display thing, or like in the car with David Bernhardt Sr., you know. He's going this fast, or she Davida I don't know. Never mind. Anyway, your favorite driver is going 50 meters per second. It's about 112 miles an hour. I think that's pretty close to fast car. Find the car's centripetal acceleration. Oh no, Mr. Barton, you never told us about centripetal acceleration. All right, let's start by finding the centripetal force, or trying to, and then we'll talk about centripetal acceleration. They're surprise, surprise, because forces cause accelerations. They're pretty similar. So let's talk about our centripetal force. Our centripetal force is equal to mv squared over r. What would be the centripetal force in this case? You've got your little car right here. That's an ugly car. Anyway, you got your car. It's going this way around the track. What's the force that's going to push it towards the center? It's going to be, if we look at our force diagram, we've got normal force from the road up. We've got the weight down. The thing, if we're looking at the back of the car, we're standing like here, looking at the back. The thing pulling our car this direction would be the friction of the tires on the road. So the friction, which is the force that is pointing towards the center, the centripetal force, must be of a certain size, otherwise it won't work. Let's think. If you don't have enough friction, what's going to happen in this car? It's going to slide and it's going to go that way and it's going to crash into the wall, and that's bad. If you have too much, it pulls you in, like more towards the center. But if it's just right, you go in a perfect circle. So the like magic just right size is this one. Okay. So our friction, which is the centripetal force, because it is the force pulling us towards the center, is mv squared over r. This is also our net force. So it also equals ma. If we want our centripetal acceleration, it's this acceleration. It's AC. So how do we get an acceleration from a force? We just divide by mass. So the masses cancel. So our centripetal acceleration is the same formula as the centripetal force. You just get rid of the mass because we divide by mass. So v squared over r. So this is going to be 50 squared over 40. This will be 250 over 4. What is that? What is that? But you guys, you should never ever make notes. When you guys grow up to be teachers like me, you should never ever make notes without a calculator sitting right next to you. It is AC equals 62.5 meters per second squared. So that's our centripetal acceleration. So just 6 times gravity. This probably would not happen. I didn't really check these numbers ahead of time. Maybe he's either going way too fast or the circle's way too small. I don't think cars can actually do 6 times gravity, right? G is 10 meters per second squared. This is over 6 times bigger than that. So this guy's pulling 6 G's like in a fighter jet or something. That's pretty crazy. When you guys are teachers like me, you should maybe also check your numbers before you put them in videos. Okay, let's do one more. This one's a little more conceptual, but it teaches a good lesson. So, you're in the garden with your dad and you're watering tomato plants. You have a bucket filled with water and you swing it over your head to freak your dad out, right? And I don't know if this is just me, but when I was a kid, I used to do stuff to irritate my parents just because I think that's just what kids do, right? Is they're like, you know what would be funny is if my dad was irritated. So you got some shoulders, and then you take this bucket, and you whirl this thing above your head. There you go. So what happens when you whirl this thing above your head is your shoulder is the center, and then it goes in a big old circle, right? If you swing this thing too slow, you're gonna dump water all over you and your dad, and that's why it's funny. That's why your dad's irritated. It's like, don't get water on me, or I'm gonna be upset. But you're a kid, so you've got to make them just upset. You know what I mean? You know what I mean? Maybe not. Maybe your parents are more or less tolerant than mine were. I don't know. But I used to try and push their buttons. So we're going to swing this bucket. Here's where the physics starts. We're swinging a bucket in a circle. Your arm is 60 centimeters long. I measured mine. Mine is 60 centimeters long. And there's 5 kilograms of water in the bucket. This is also 5 liters. Fun fact, 1 liter of water is 1 kilogram. How fast do you need to swing the bucket so the water doesn't fall out? Let's kind of talk about the reasoning or logic behind the problem, and then we'll do the problem. Okay. So we want to know how fast is it necessary, which means we're kind of looking for like the minimum speed. What's the slowest I could swing the bucket without the water falling out, right? If I swing it too slow, so it's like it's here, right? And then 1 second later, it's there. By the time you get 1 second here, 1 Mississippi, all the water has already fallen out of your bucket, which kind of sucks. But oh well. And then your dad's here, right? All like hunched over, digging in the garden and whatnot. And now he's covered in water. Ha ha ha. Funny, funny. Dad got wet. Okay, so if we swing it too slow, the water falls out. Conversely, if you swing it too fast, your dad's not going to get irritated because the water won't, it's not even close to falling out, right? You could like whip this thing around really fast, and then it feels really heavy. It like yanks on your arm really hard, and the water doesn't fall out, and it's like plastered to the bottom of the bucket, right? So let's examine maybe the interesting spot up here when the bucket is vertical, and that's where we want to look at our water. Okay, so here's our bucket, and it's vertical. For the water to stay in the bucket and to go in uniform circular motion, okay, the force towards the center of the circle must equal, or it is a centripetal force because it's pointing towards the center, and it must equal mv squared over r in order to stay in the bucket. Okay, but the centripetal force is not a force in and of itself. Some real force must be applying the force. You feel me? Like gravity, right? So let's draw a force diagram for our water. For our water, here's our force diagram. We have gravity pulling the water down. That's why it might fall out of the bucket. Wait. Okay. The solid bottom of the bucket is on top of the water when the bucket's at the top. So perpendicular from the bucket towards the object that's like touching the solid thing would be this way. So we also maybe have a normal force from the bottom of the bucket pointing also down towards the ground. Okay. If I swing the bucket really, really hard, the water wants to fly this way. It wants to, like if you let go of the bucket is going to go that way. So you need a force to pull it back down into the circle. Gravity wouldn't be strong enough, so the bottom of the bucket is there to help push the same way the car is in your way, pushing you towards the center. The bottom of the bucket is in the way of the water, helping push it down towards the center of the circle. So if we swing too fast, the normal force gets really big. If we swing too slow, then our gravity is stronger than the centripetal force, and it's not the right amount to go in a circle. It's too much, so it goes in too tight of a circle, right? And it falls down towards the center of the circle. It falls out, basically. So we want our centripetal force to be equal to the force of gravity. If it's equal, then it is the perfect speed so that the normal force is 0 and gravity is just kind of like helping it keep going. This is maybe a bit confusing, but trust me on this one. The perfect one is when the only force acting on the water is the force of gravity, and that's it. And you can kind of think of it like we can reduce the normal force by swinging slower, but we can't get rid of gravity. So if it's not going in a fast enough circle, then it's going to fall out of the bucket. And that's kind of where we're going with this. So we just said equal to the force of gravity, which is weight, which is mg. So here's the physics. The physics is easy, or the math is easy. mv squared over r equals mg. The m's cancel. So I gave you that there's 5 kilograms of water, but this will work with 100 kilograms of water or no water or anything. It would work with an empty bucket, right? Which is kind of interesting, I think. All right. So we want V. How fast do I swing the bucket? So times R. The radius is 0.6 because we want it in meters because G is going to be 10 in meters per second squared. So we need this in meters, so 0.6. So we have V squared over 0.6 equals 10. Multiply 0.6 over. So V squared equals 6. And then take a square root. What's the square root of 6? Let's use that calculator that I definitely have laying right here. So the velocity, the slowest you can swing the bucket, is 2.45 meters per second. If you swing it any slower than that, the water will fall out of the bucket and then get you and your dad wet, and then you're going to be grounded. No more fun. All right, cool. So hopefully this was fun and enjoyable. If not, I don't know, complain to my manager or something. Don't dislike my YouTube video, though. If you do that, my engagement numbers are going to go down. Don't unsubscribe. I need you guys. If I don't have you guys, I don't have anybody. Actually, I'm married. I'd probably be fine. But, you know, I'd prefer if you didn't unsubscribe. I prefer if you liked and subscribed. That'd be great. Until next time, have a wonderful day. I'll see you guys.